Hey guys, welcome to another A-level maths revision video. In this video today we're going to take a look at graphical methods in kinematics, so we're looking at mechanics. This is a pretty brief topic, so I've not picked up a massive amount of questions, and they're not particularly long questions, but it's worth going over in a separate video. So let's take a look at these questions. This first question is quite a nice one to start with. It's definitely not the easiest question, but it shouldn't be too challenging, more kind of like a little bit of a proof question. So we've got this context here of a car moving along a straight horizontal road. So we know at time t equals 0, the velocity of the car is u meters per second. It then accelerates with constant acceleration, a meters per second for t seconds, and the car travels a distance d meters during these t seconds. Now, we're asked to use the graph to show that the distance d is equal to ut plus a half at squared. Now, remember when we're talking about distance, so distance d, that's equal to the area under the graph. So it's the total area under the graph. Okay. Now, if it's equal to the total area under the graph, what I'm going to do, I'm just going to draw a few little lines on here just so we can see what we're looking at. So this should be, so that's t there. So that's the point t. Now I want this area, so what I'm going to do, I'm going to split this up into a triangle. So it's not going to be perfect. Oops, we've got a bit wonky there. Right there. So that's my triangle. So if I can work out the area of this triangle, this right angle triangle, and I can work out the area of this rectangle, combine them, we should be able to show that d is equal to ut plus a half at squared. Now before we actually start looking at any areas, all I'm going to do, I'm going to define this point here, the highest point, my final velocity here, as being I'm just going to call it h, but it doesn't actually matter what you call it. You can call it any letter you want. So this point here, okay, I'm going to call that h. Like we said, it doesn't matter, and you'll see why in a moment. So let's work out the area of the rectangle first. That's nice and easy. So the area under the graph, well, let's work out the area of the rectangle first. Well, that's going to be the full length of the base, so that's t, times by the height, u. So that area is simply going to be ut. Okay, which is exactly how it starts, d equals ut. So the first bit's looking good. We need to obtain this a half at squared now. Well, we need to work out the area of the triangle then. Well, that's going to be a half. So remember, for the area of a right angle triangle, you're going to divide base times by height. You're going to divide that by 2. So the base here, well, that'll be t. My height, so the height of this triangle will be h minus u. Okay, so the area of the triangle then is a half times by the base t times by the height, which is h minus u. Okay, well, we know this straight line here, so we'll just draw it on the sketch. This straight line here, this is my constant acceleration here. So in other words, a is equal to h minus u divided by t, the time. Okay, so it's the change in the velocities here divided by time. So if we know a is equal to h minus u divided by t, well, the only issue we have here now then is this h minus u. So the area under the graph is a half times by t times by h minus u. But like we just said, this h minus u is an issue. However, if you notice, this where a equals h minus u divided by t, if we arrange this to be h minus u equals, then we get at is equal to h minus u. And if we just substitute that into here then, what we get is ut plus a half times t times, where h minus u is equal to at, so we times that by at. And if we simplify this then, so this is the distance d is equal to ut plus a half, t times at gives us a t squared there. Okay, and that's exactly what we wanted to show there. Okay, so d is equal to ut plus a half at squared. Like it said in the question, you can't use any of the kinematics or the SUVAT formulas listed in the formula book. So you've just got to be very careful there. Use the graph, and remember the distance is equal to the total area under the graph there. Okay, so that's a nice question just to get us started. The next question then, again, just making sure you understand what happens with these kind of graphs. So this graph here is a speed time graph. It's just a cyclist moving on a straight road. So the first part A, just asks us to basically say what happens between t equals 0 to t equals 3. What's important about that being a straight line? Well, that straight line then, so what we're looking at here is this point here, this straight line. Remember, this straight line just implies, or it doesn't imply, it just tells us that there's constant acceleration. So the cyclist has constant acceleration. Okay. So constant acceleration there for part A. I'm just going to carry on in red. Part B. So from t equals 3 to t equals 7, what's important about this line being parallel to the t-axis, so the time here? So we're looking at this part now. So what's important about this being parallel to the t-axis? Well, this just means then that they have a constant speed, okay? So in that case, they have constant speed. Okay, constant speed then. And then for part C, this is where we're going to have to start working some actual maths out here now. We're going to find the distance travelled by the cyclist during the 7-second period. Well, just like the previous question, when you're looking for the distance, remember that's just the total area under the graph. Okay, so that's going to be all of this here and all of this here. Okay, so what I'm going to do is I'm going to look at the area of the trapezium, work out the area of this rectangle here, add them together, and whatever that comes to, that's our distance. So, part C then. Well, the rectangle, hopefully, is nice and easy. The base would be 7 minus 3, so that's 4, times by the height, which is 5. So, area of rectangle, that's equal to 5 times 4. Okay, so that gives us 20. Not going to bother with any units just for now, just write the area down, so that's 20. Now we need to work out the area of the trapezium. So area of trapezium. So I'm going to add up this height here, so from the origin to 2, and then again add up the other parallel height. So if I just draw in a different colour so you can see. So this height here plus this height here. Remember, we divide that by 2, and then we times it by the base here, which is 3. So that's going to be 2 plus 5. We divide that by 2, and then we times that by the base, which is 3. Okay. Work that out, that'll give you 7 over 2 times by 3, which would be 21 over 2. So, in that case, all we need to do now is add up these areas together. So in that case, the total area is the sum of the areas. So that's going to be 20 plus 21 over 2, which if you do it on your calculator, will just give you 30.5. And with it being distance, the units we're using here is meters, so 30.5 meters. Okay, so total area, 30.5 meters. Again, one of the key ideas here is that the distance is equal to the total area under the graph. This is a very common theme that you will see, come up quite a lot. So just be aware of that fact. The next question then, this is one of these questions where you actually have to sketch your own speed time graph. So let's have a look at this one. So we've got a car that moves on a straight horizontal road at time t equals 0. So this, what we know here is that the speed here will be the initial speed, and which we're told is 20 meters per second. And that's at the point A. It maintains this speed for 20 meters per second for 25 seconds, and then it moves with constant deceleration of 0.4 ms to the minus 2. Now it reduces that speed from 20 meters per second to 8 meters per second, and then it moves with constant speed 8 meters per second for 60 seconds. Then it then moves with constant acceleration until it's moving with speed 20 meters per second. So that's a lot to go off just all at the beginning. So let's break it up step by step. question 4 here, part A. So again, use a ruler for this. I'm doing it freehand, so it's a bit all over the place. As long as you can see what's happening, that's the most important thing. So this will be my initial axis here, and this will be time. So at time t equals 0, my initial speed, we know that's 20, so that would be, say, here. So let's just say that's there, 20. Okay. So we start with initial speed 20 meters per second, and it maintains that speed for 25 seconds. So this is just going to be a straight line then, because it maintains that speed for 25 seconds. So let's just say that's there. Okay, it doesn't have to be precise. It's just a sketch. Okay. Now I'm just going to jot this down just so we can see where we're working from. Okay. The car then moves with constant deceleration of 0.4 meters per second, and its speed goes from 20 meters per second to 8 meters per second. So now, from this point here, we're going to go down with deceleration to 8 meters per second. Okay. Okay, so let's just say that's there. So at this point here then, this is 8 meters per second. And now, let's go from here. The car then moves with constant speed, 8 meters per second, for 60 seconds. So, from this point here then, it carries on for another 60 seconds at this same speed. That's going to be a straight line. Let's just say that's there. And then finally, the car then moves with constant acceleration until it's moving with the speed 20 meters per second. So remember, constant acceleration, it's going to be a straight line, looking something like this until it gets to 20 again. Okay, so we'll say that's there. Okay, again, just a rough sketch, but just to give you an idea there of what's going on. Okay, so that's our rough sketch there. It's not brilliant, but hopefully it now makes a bit more sense on how to sketch a graph like that. And then for part B, we're just asked to find the time for which the car is decelerating. So remember, this deceleration occurs here. So now, remember, this is kinematics. So these graphs are always linked to your SUVAT equations. So in that case, we can actually use our SUVAT equations here to work this out. What we've got here is an initial speed, 20. We've got the final speed, 8. So using that now, let's work this out. We've also got the deceleration of 0.4. So in that case, what we can use here is V equals U plus AT, because all we're looking for is what T is, the time. So V, that's our final velocity, so that would be 8. Is equal to U, our initial, so that's 20. A is, it's deceleration of 0.4, so that would be minus 0.4 here. Minus 0.4 times T, which we don't know yet, which we're going to work out in a moment. So what I've got here then is 20 minus 0.4T is equal to 8. And this is just a nice linear equation to solve. To make life a bit easier, I'm going to take this minus 0.4T onto this side, so it becomes positive, and subtract 8 off both sides. So we get 0.4T is equal to 20 minus 8, which is 12, and therefore finally, dividing both sides by 0.4, we get T equals 30 seconds there. Okay, 30 seconds there for the time. So hopefully that makes sense. Always be aware of the fact that we can usually always use our SUVAT formulas, our SUVAT equations to help us if we do need to find anything like that. Okay, so that's that question done there. Now finally, this question here, Jan 2010, we've got an athlete that runs along a straight road. She starts from rest and moves with constant acceleration for 5 seconds, reaching a speed of 8 meters per second. She maintains this speed for T seconds and then decelerates at a constant rate until she stops. We're told that she's run 500 meters in 75 seconds. So again, first part, we want to sketch a speed time graph for this. So let's have a go at this. It's nothing perfect, but, you know, again, just so you get the idea here. So she starts from rest, so what that means is the initial speed is 0 if she starts from rest. So we're going to start down here. She has constant acceleration for the first 5 seconds, reaching a speed of 8 meters per second. So let's just say A is here, okay? And let's just say this is 5 seconds there. So at 5 seconds, she's got a speed of 8 meters per second. Okay, so that's that constant acceleration there. We then know the speed is maintained for t seconds. So this would then be a straight line for t seconds. We just don't know what t is. So let's just put that in. So let's just say that's there. Okay, so that's 5 seconds. This would then be t plus 5. If it's t seconds along, and we start from 5, this would be t plus 5 here. Okay. And then she decelerates at a constant rate until she stops. Okay, so then she comes to rest at a constant deceleration here, and that's in 75 seconds. So that one there is 75. Okay, so again, my sketch isn't particularly good. Use a ruler and that, make it look neat. But there we go. So that's the general idea there. But now we can actually work out the value of t. The key idea here, again, we're given the total distance that she's run. So if we know the d, the distance, is 500 meters, so d is 500, and we know that distance is equal to total area under the graph. In that case, then, what we can do is we can work out the value of t here. So how do we do that? Well, again, what I want to work out is the area of this right angle triangle here, the area of this right angle triangle here, and then I'm going to work out the area of this rectangle here. Okay, so this first triangle here, we've got a base of 5, height of 8, but then we're going to divide the product of that by 2, so 8 times 5 is 40. Dividing that by 2 then, that's going to give us 20 there. Okay, if we do the rectangle here then, what's that going to be? Well, that's going to be the distance from 5 to t plus 5. So that will just simply be t, right? If you do t plus 5 minus 5, you just get t. So that distance here to here, that's t. So that's going to be t. So it's going to be t times by the height, which is 8. So t times 8. And then finally, if we deal with this final triangle here, again, looking at the area of that, we need the height, which is 8, times by the base. So the base will be 75 minus t plus 5. So that's 75 minus t plus 5. And we times that by the height, which is 8. And we divide the full thing by 2, because it's a right angle triangle. So now, all we need to do is simplify here and work this area out. So if we do it up here, so the area, that will be 20. T times 8, so that's 8t. And then finally over here, 75 minus t plus 5. So this is, sorry, so this should be 75 minus t minus 5 here. If you're subtracting the full thing off. So that gives us 70 minus t. So that's 8 lots of 70 minus t divided by 2. However, if you've got 8 lots of this and you divide it by 2, it's just the same as times in the first thing by 4. So what we'll do is we'll times the full expression by 4 then. Okay, and we know this area, the distance is 500. So this full expression here is equal to 500. So if we just simplify this linear equation and solve it, we obtain our value for t. So 20 plus 8t, 4 times 70, so that'd be 210. Oh, sorry, 280. I can't do basic maths. And then 4 times minus t would be minus 4t. That's equal to 500. And then if we just solve this, 20 plus 280, that's 300. AT minus 40 is 4t then. This is equal to 500. So all we need to do then is isolate the t here. So if we subtract 300 off both sides, we get 4t is equal to 200, subtracting 300 off both sides, and then finally divide through by 4. And 200 divided by 4 gives us t equals 50 there. Okay. And there we have it. So like you can see, sometimes there's a little bit more work involved, like we can see for this final part B here. But overall, this shouldn't be too challenging of a topic. It's considered first year material. You know, so it's just kind of follow up from your SUVAT equations. But hopefully this has helped. If there's anything that's unclear, if there's any mistakes that you can spot, like always, just let us know down below. Cheers.